Hi, students. If you're watching this video, there is one more step in writing Lewis dot structures and picking the preferred structure. And this particular step talks about when, in some cases, with the central atom, even though it has an octet, it's going to prefer to expand that octet to reduce the formal charge. And that's what this video covers. It's actually step 6 of that handout. So, expanded valence. What do I mean by that? If I have more than an octet, right? So where do I get this rule for octet? Well, the noble gases, right? They have their S and P sublevels filled. That's why they get an octet. One orbital in S, 2 electrons, 3 orbitals in the P sublevel, Px, Py, Pz. That's an additional 6 electrons, 6 plus 2, 8. But again, when we're in the third principal energy level, now we have the 3D sublevel, which allows me to expand the octet. And that's where that bonding pattern video that I had earlier discussing hypervalency comes into effect. So when you have d orbitals, you see in a lot of cases, phosphorus when it's a central atom, sulfur, chlorine, bromine, iodine, krypton, xenon, when they're central atoms, they actually expand the octet. And yeah, even noble gases. Now with chlorine, bromine, and iodine, if they're an outer atom, they're going to follow the octet rule. They're going to be happy just having the 1 bond and 3 lone pairs. So really, you're looking at this expansion of the octet when it's a central atom, and I have a central atom that's either in the third energy level, principal quantum number 3, period 3, or beyond. So in step 6, if central atoms in principal energy level 3, 4, or 5, consider expanding the octet to reduce the formal charge magnitude. So we're going back to steps 4 and 5. So let's look at sulfate. So if we look at sulfate, right, in your general chem courses or your intro, 6 valence electrons for sulfur, each oxygen is 6. There's a negative charge, so plus 2 electrons. What is that? A total of 32 valence electrons. And sulfur would be in the middle. You have your oxygens. Okay. First thing you got to do is you got to make sure everything's bound. So 4 bonds, I used 8 electrons. So now I have 24 electrons. What do? I attach them to outer atoms to satisfy octets. Okay, so now I'm using up my, 24 electrons. There's no more electrons. If there were more, we would attach them to the central atom sulfur, and sulfur could accommodate more than an octet because it's in the third principal energy level. But we don't have that problem. We don't have the problem of needing to attach more to the central atom. But we do still have a problem. And what people don't realize is, yeah, in your introductory and preparatory chem, you'd be done with because sulfur has an octet. But this is general chem, and we can expand our octets. Why? Hypervalency, and this is in a principal energy level of 3 or greater that has a d orbitals. So when I use formal charges from step 4, and watch those videos, this has a formal charge of -1, -1, -1, -1. And the sulfur, I'll do that because we haven't done that in the formal charge earlier videos. This particular sulfur's formal charge, right? So sulfur's formal charge, it has 6 valence electrons, -4 bonds, -0 electrons in lone pairs. This sulfur's formal charge is equal to a +2. Okay. So what I end up having overall, right? Every oxygen has a -1, the sulfur has a +2. So overall, the formal charge is a -2, which matches, the charge of this polyatomic ion. But step 5, what do we want to do? And step 4, we want to minimize former charge. So when you have a central atom that can expand the octet, what you can do is actually take a lone pair And for every +1, if you add a bond, it'll reduce the magnitude of that central atom by 1. So by me taking a lone pair from 2 oxygens, it'll make that sulfur have a 0 formal charge. So let's see what that looks like. So if we look at this now, we can do the formal charge counts, and we've already seen the counting of oxygen. This is -1, this is -1. If oxygen has a single bond, 3 lone pairs, formal charge -1. But oxygen likes to have what? 2 bonds, okay? So 2 bonds, 2 lone pairs, formal charge of 0, formal charge of 0. And then if we count sulfur, right? The formal charge in this structure, it has 6 valence electrons and 6 bonds. 1, 2, 3, 4, 5, 6. So it has a formal charge of 0. And sulfur wants that formal charge of 0. And why is that? Well, it can accommodate the 6 bonds. Why? Because it's in the 3D, it has a 3D sublevel. It's group 6A. Remember, 6A likes 6 bonds, just like 5A likes 5 bonds if it's phosphorus, just like 7A chlorine likes 7 bonds. So this has 6 bonds, which is one of those preferred bonding patterns because it gave me a formal charge of 0. And this is actually still a 2 negative for the sulfate oxyanion. Where are the 2 negatives? On the oxygens with only single bonds. And this is the preferred Lewis structure. The other thing that this helps us see is why sulfuric acid is a H2SO4 rather than an H4SO4, right? Why? Well, if we left it like this, where every oxygen has, a formal charge of -1, nothing's really happy, right? But if we leave it with an expanded octet and minimize the formal charge, those additional hydrogens can come here and form a bond right here. And what I'll end up having for sulfuric acid whoops, is if I look at this, every oxygen has 2 bonds and 2 lone pairs in sulfuric acid. So how do I get the sulfide ion? Well, this bond, remember, is extremely polar, and the oxygen, once I throw it in water, is going to steal that electron from hydrogen and make this negative charge. So very powerful. Lewis dot structures help us understand structure, and structure helps us understand properties, and it also helps us understand now the formulas of these polyatomic ions as well. So thanks so much for watching, and I appreciate it.